Hello everyone, my name is Jae-Seok Yang, Principal Geotechnical Engineer from MIDAS IT Headquarters. Today's session is on the soil structure interaction for pile Raft foundation. For soil structure interaction, we need two groups of engineers, structure engineers and geotechnical engineers. We are going to cover different soil structure interaction methods, what are the different approaches available and the different efficiency levels, benefits, and so on. This is an overview for today's session. First, I will briefly walk through the soil structure interaction concept. Then, I will overview the substructure, which is indirect method. And then, I will present about the calibration and the direct interaction method. Lastly, I will introduce a case study. The phenomena in which the response of soil and movement of the structure influence each other. When external forces such as earthquake act on these systems, neither structural displacement nor ground displacement are independent of each other. Unlike an above-ground structure, the response of an underground structure subject to an earthquake is mainly controlled by the ground displacement. The ground displacement, in turn, is largely influenced by the dynamic properties of the ground and its modeling method. The ground exhibits a complete nonlinear behavior depending on the strains developed in the ground due to the dynamic load. It is therefore important to closely examine the nonlinearity of the ground relative to strains. The substructure method is based on the principle of superposition separating the first two causes of the interaction. The inability of the foundation to follow the free field displacement and the effect of the dynamic response of the structure foundation system on the movement of the supporting soil. This method is limited to analysis for linear system or linear equivalent because it is based on overlays. The method proceeds as follows. First, calculating the free field response of the site without any embedding of the structure, and analyze the soil deposit as a dynamic subsystem. This response will be obtained in the nodes where the structure will be inserted subsequently, determining the force displacement relationship. The soil dynamic stiffness coefficient can be physically interpreted as a spring damping system. This stage corresponds to the evaluation of kinematic effect, so that the structure and foundation lack masses but have rigidity. In the second step, the structure supported by this spring damper system is analyzed by a load case that depends on the free field movement. That stage corresponds to inertial interaction, hence the mass of the structure and foundation if considered. Whereas in direct method on your right hand side, the soil structure system is modeled and analyzed in a single step. The excitation movement of the free field is carried at the base and at the boundaries of the models, and the result of the response of the interaction system is calculated from the equations of motion. This method requires computational program that can treat soil and structure behavior with the same rigor. For this, it is necessary a finite element program or a finite difference. In this method, the structure can be modeled in a simplified way, but then it is necessary to remodel the structure more precisely in a second stage, where the result of the motion is applied at the base of the structure in order to determine the detailed answer. Therefore, the programs used for this analysis must be computable. Now I will overview the substructure, which is indirect method. Structural engineers use spring to represent the soil as we see. For a given column load, The foundation reflects representing the soil settlement and the spring represents the soil pressure. On the other hand, geotechnical engineers model the soil as a continuum, either as an elastic space or an inelastic space, to determine the corresponding soil settlement and stress due to the column load. Determination of what the soil springs are, especially under the left. The K value, as we refer to it, which is also known as the Winkler spring or modulus of subgrade reaction, is the ratio of soil pressure over displacement. So the unit is pressure or stress over length. Now the foundation response. The significant difference between Winkler and continuum model is as below. This can be demonstrated easily by examining two extreme situations, a rigid foundation and a flexible foundation. You will see the contact pressure and settlement between these extreme situations. For the case of the rigid raft, on the left-hand side, we have the structural approaches of Winkler springs model, and is a single set of Winkler springs, which is on uniform settlements and the uniform stress distribution. However, in geotechnical approaches, as you can see, in the settlement may be constant, but the stress distribution is not. The high stress developing at the edge of the left. Now, by the definition of the springs at the edge of the left have to be higher than the springs at the center of the left to capture this stress behavior, while you have higher stresses but the same settlement. Now, in the case of the flexible raft, in the left-hand side, you have the case of the single set of spring, which gives you uniform settlements and uniform stress distribution. However, elastic theory shows that the stress distribution under the left is going to be constant as the post that we had at the previous case, but the settlements are going to vary. The highest settlements are carrying at the center of the left and the smallest settlement carrying at the edge. Again, based on the definition of the Winkler springs, you will expect higher springs at the edges and lowest at the center. So what is the solution for this? The solution is that we should not use one zone of springs, but at least two zones, with the outermost springs being higher than the springs at the center. Now, for steep soil, outer springs may increase from 30 to 40% compared to the springs at the center, whereas at the soft soil, we will have to increase 2 or 3 times compared to the springs in the center. Again, the steep soil and the soft soil is relative to the foundation stiffness, and the loading and even rock would need to use 2 zones of springs. Different method to determine the K value, also known as modulus of subgrade reaction. Method A consists of plate load test. You calculate the values from the test stated in your textbooks. They are not appropriate for the raft design because they only apply to the areas at 1 foot by 1 foot scale. Method B consists of taking the same values and is a crude method. The most appropriate method is method C, where you will model the loaded foundation probably with finite element. Now for method C, how you could do that is geotechnical engineer will estimate the settlement and bearing pressure at many points within the raft, and they will determine many K value based on the pressure of settlement designs. And they will draw contours of the K value and determine accordingly what kinds of zones to assign and what kind of K value assigned to these zones. This is the method that most structural engineers are most familiar with, either using a finite element analysis software or a simpler design software for most cases. structure engineers reflect the soil and soil structure interaction using soil spring data. There are largely two ways for the indirect method too. Handling the substructure apart from the superstructure with the superstructure information reflected using the load or boundary conditions applied to the top of the substructure. Second, handling the entire structure together, meaning superstructure and substructure together. The first, the substructure only approach is the common approach taken from a design software such as RCPR, LFile, and FVPR. However, when we have to consider the soil structure interaction, it may affect the superstructure as well. Therefore, we have to understand that with these substructure only approaches, we are working with broken components for the whole system in reality, especially if we are dealing with seismic analysis. The second, the entire structure together approach is more common and more accurate approach taken if an engineer is using an analysis tool such as MIDAS Civil or MIDAS Gen. The second model, bridge with all of the superstructure and substructure together, can be time-saving if any engineer would like to perform direct interaction check, which I will introduce today. It is because this whole bridge model and data can be transferred to MIDAS Geotechnical software, GTS NX. We'll get to the direct analysis in a little bit. Now I will present about the calibration and the direct interaction method and compare the result between the different SSI methods. Pile Raft and their bearing behavior is a very good example for soil structure interaction. If we have a look here on the left side, we have a raft separate from the piles, so the raft itself has its own interactions with the soil around it, and the pile has interactions with the soil around it. And there is interaction between the pile, the raft, and the piles themselves, which is a little bit summarized here on the right side. These four arrows showing the interaction, we have pile soil interaction, we have raft soil interaction, we have raft piles interaction, and we have pile interaction. These interactions are very critical, governing how the pile raft will behave or perform and its bearing capacity at the end. The total bearing capacity of the pile raft will be the summation of the bearing capacity of the piles plus the bearing capacity of the pile raft. And the pile bearing capacity is in itself the summation of the base capacity plus the shaft capacity. The raft bearing capacity is at the contact stress over the area of the raft. And this total bearing capacity combined by a raft should be larger than the applied loads multiplied by the factor of safety. What will be requirements of a realistic numerical model for pile raft? The model should be able to consider the three-dimensional behavior of a pile raft foundation, so we need to think in 3D for that. The applied constitutive laws should be able to take into account the nonlinear pile soil behavior at pile raft and pile base, and the stress-strain behavior of the soil depends on the applied stress path and strain level. Therefore, the applied model should be able to take these effects into account as well. So, both constitutive laws govern the pile-soil interaction, and also the soil behavior itself should be capable to handle these interactions. The model should be able to simulate the behavior of a single pile to check its reliability and to adjust the applied parameters depending on the chosen pile type. Here we refer to what we call calibration process. So, if we have result from a pile loading test, you should be able to simulate this file loading test properly in your numerical tool. And then once you are able to capture the behavior you have in the file loading test, you can go back and apply or utilize these parameters you are using in your full structural numerical model. Applied model should be able to consider the different interaction that govern the behavior of the file Raft, which we just saw in the slide. The workflow typically to model file Raft will start by creating the numerical model and filling this numerical model by input parameters from geotechnical reports, from lab testing and field testing, and also from file loading test. So you probably will create a single file model, calibrate parameters for this file model, and this will be using for feeding your final of your numerical model of the complete file Raft. You are on your simulation and you will get result and terms of determination, stress and strains, forces in the files, and you can also time refer parametric study. So variation of the layout of the file, the diameters and lengths and properties, and also different load combinations. If you have different combinations, refer to structural load, wind load, earthquake load, and combination of these. At the end, you always end up with a set of structure parameters that you come up with, and if you do the separate structural design most of the time, you have this to the structure engineer to use it for structural design of the superstructure. And there are always interaction between structural engineers. You will go back and modify your model a little bit. So this is a typical flow chart for the numerical analysis for file Raft foundation to enable structural design. So to quickly determine the iterative process between the structural engineer and geotechnical engineer, the structural engineer provides the column rows to the geotechnical engineer, who has already developed and model of the foundation and the soil, and the geotechnical engineer evaluates the foundation settlement and stress and provides the structural engineer with winkler spring or soil springs. Then structural engineer runs their model and they determine the foundation settlement and the stress under the left. They compare with the geotechnical engineer and either they are closing up or the geotechnical engineer needs to revise the springs and come up with the new foundation settlements and stresses. This process keeps up until the settlement between the structural model and geotechnical model are closing up. When we come to GTS NX, we can model files with three different approaches. Actually, in general, in 3D numerical tool, you should be able to model your files as a volume element, and you should have proper interface around it to be able to capture this interaction between the file and the soil properly. So this is a basic ingredient you should have. In GTS NX, we can do that. We can model the file as a full volume element, solid element model with an interface around. When you have larger number of files, it can be computationally intensive. So you can think about alternatives, and one alternative to use beams represent the files with an interface around it also. Or you can use something like we have here in GTS NX, embedded file or file element, which is a line to solid, which is a beam element connected through a line to solid interface to the surrounding soil. You look close to each of these elements. So if you look here at the soil model, we imagine here we have a file inserted in the soil. File itself is modeled with solid element, which is a volume element filled by its full diameter and length of course. And next to the file itself, we have 2D interface surrounding it to be able to model the soil structure interaction. We have the solid for the soil, solid for the files, and we have interface connecting a file to the soil. To such a model, you have to ensure that you have nodal connectivity along the whole surface of the file and surrounding soil and the interface as well. That means that you also have to think about refinement around the file to be able to capture the stress equalization that may happen if you have some failure. So if we have a large model with large number of files, that becomes a huge model computationally, takes a lot of time, even with the hardware development nowadays. The interface we have around this file, surface interface element, this can be linear, can be quadratic, and they will able to capture your soil structure interaction behavior properly. This interface can be linear elastic, non-inelastic, and can be also plastic with Coulomb friction of interface. Now, we will provide all these possibilities, even user-supplied interface property is allowed. Other possibility is to use beam solid connectivity model, and here you will have solid represent soil, and for the file, instead of using solid element, you will use a beam element. Here we have only cross section showing, so this is for visualization only, but the file itself is actually modeled with a beam element, which is 1D element. This beam element is fully connected to the soil around. We have to have fully compatible or full nodal compatibility between this beam element and surrounding soil. And you can have an interface, so 1D interface connecting this beam element to the surrounding soil. So again, the nodal connectivity still has to be ensured. The nodal compatibility requirements makes geometry modeling and meshing of the soil elaborative. You will have less number of elements because all the 3D file elements became 1D and for file left with large number of files. This technique produces large models and you still have to ensure this compatibility. On the other hand, you will have forces and moments in your file as output immediately. So this is another option. The third option we have is to use this embedded file or file elements, and in embedded file, you don't need to worry about the nodal connectivity between the file itself and the surrounding soil. So you can model your soil completely independent of the files, and the files themselves can be placed arbitrarily in these soils going through the solid element. The beam elements that represent the file will be connected to the surrounding soil through a special interface. Actually, two interfaces. One is line to solid interface for the shaft, which is in itself two parts. One part is connected to the beam. One part, here I lighted in red, connected to the hosting 3D soil element. Here I have to mention of this idea having embedded file techniques goes back to the beginning of 2004. There was a publication by Sadek and Sauer. They had a word on 3D embedded beam element for reinforced geomaterials. It was meant that for reinforcement like anchor and things like that, and this was utilized here as a file element. So there was some modification, mainly addition of the interface and the tip interface, and the tip element to become a file element. Here shows the line to solid element for this beam to solid connection, and you can see here that can be used with different type of elements. We have hexahedral, pentahedral, and tetrahedral, and the file we go arbitrarily through the element, and the GTS NX will automatically create or calculate these interactions between the file element and the hosting soil element. The soil element can be linear or could be quadratic as well. The main idea of here is that any of these solid element displacement field is known anywhere inside the element. The declaration function will allow you to calculate this space anywhere in the element. And once the interaction position is known, the displacement at the nodes of these files intersecting soil element can be calculated. The same goes for the interfacing between the hosting element and the beam element of the line-to-solid interface. Characteristics of line-to-solid interface that the file and the soil geometries and meshes can be specified independently, so you don't need to worry about messing them and having nodal connectivity. The intersection applied solid elements are calculated automatically. You can assign nonlinear friction slip properties for the line-to-solid interface element, and I will explain that just in a few slides next. Mesh refinement requirements for the soil are minimum, so we have reduced computation time. This is really well suited for file left type analysis. Next to the shaft, we have a similar element spring, which is nonlinear spring at the tip. So the tip again can be arbitrarily placed of any part of the hosting soil element, and you can have an interface. Point solid interface in this case, describing the relative behavior between the soil and the file tip. This table is a comparison of three approaches for shaft friction. This table is a comparison of three approaches for file tip capacity. Automatic creation of line-to-solid interface elements in GTS NX. After meshing file lines with a single beam element profile, use the file tip menu. Create an property for the file soil interface behavior, and define the file soil friction properties and file tip bearing capacity. In terms of input parameters, these interfaces between embedded file of the beam and the soil are characterized by few parameters. In principle, you have a set of springs. You have a set of springs at the shear between the beam and the soil, and these springs are two in lateral directions, so Ks, Kn, and Kt, and one along the file axis, which is Ks. The next to the stiffness, there is an ultimate shear force. Actually, the bearing capacity in this case is a sort of an input. So you determine ultimate shear force for the skin friction and also for the base capacity as an input of your model. You will not be able to calculate the failure behavior of your files. So this is really well suited for deformation behavior and subdistributed limit state. So this ultimate shear force, you need to get it from, if you have a file loading test from the curve, you can separate the shaft friction from the base and the base from the total load deformation behavior and assess your ultimate shear force for skin friction. Stiffness are actually linear elastic penalty stiffness, so they can be assigned as a high value of stiffness, and you only need to ensure that in the shown elastic part, if we look here at the graph on the left side, which describes shaft friction force in relation to the relative slip displaced between the file and the soil, we see that this elastic part until we reach the ultimate shear force. The stiffness have to ensure that you don't have the behavior of the interaction, or this interface doesn't cover the total behavior. So you should get your elastic behavior more from the soil surrounding until you reach your ultimate shear force that you have specified. So you have Ks, elastic linear penalty stiffness along the file describing the skin friction, and you have two penalty stiffness in the transversal direction. These types of files are designed in principle for axial loading. That is why you see the ultimate shear force and the Ks and the longitudinal direction, which is axial direction of file. However, in the lateral direction, there is nothing preventing that you can also apply at lateral loads. However, there is no limiting force in the lateral direction. That means minimum or limiting lateral capacity will come from the soil itself and not from the file interaction. So if we look more closely, here we will represent by this solid black line of, of the beam element, and around there is the interface. We have the Kn and Kt, which are lateral stiffness, and we have the Ks along the longitudinal direction. The traction are related to the stiffness, so the Ts, Tn, and Tt are value, so they equal to the Qs, which is shear force divided by the length. That means that it equals to the Ks, which is the stiffness to the input multiplied by its relative displacement between the soil and the file, and these are in the different direction. The Ts, which is an actual traction, and the shear traction should be less or equal to the Q ultimate that has been input in your model. The same goes for the base or the tip bearing capacity. You have the QB, Q bottom, which equals to the K bottom, which is the base stiffness multiplied by delta U, and this has to be less or equal to the Q bottom ultimate, which is a value for tip bearing capacity input, again for your model. Although we have all these springs by linear relation, you still, because we have so many points and so many springs along the whole length, and we have interaction between this beam and the soil surrounding it, you end up having higher linear curve describing force displacement behavior of the single file. This graph is also covering both positive and negative directions. When you input this relation, GTS NX actually describing the full graph in the plus and minus will allow you to capture both positive and negative skin friction. So if we have parts of the file and the behavior was negative skin friction, you can still capture that in this relation. So these are the input of the interface of the file. The traction are actually output of your analysis. Next to that, you have file beam properties, which are across section properties, material properties, and ranks. For example, you can choose from a library of cross section, the shape of the file, and input the dimension, and it will calculate section properties for you. We did a validation for this when it was introduced to GTS NX, and we tried to resimulate one of the examples where there have been extensive monitoring these days, and all the example is file of all the highway bridges in Germany, those presented by El Musrami in 1999. It shows the full file load that demonstrates deformation behavior, the total load, skin friction, and the base load. And we have simulated the exact same file behavior. So the file is actually 1.3 meter diameter file and 9.5 meter length. We have simulated this using embedded file technique, and we are satisfied with the behavior we could capture, the total load behavior, skin friction, and the base resistance. We can say that we can capture in a reasonable way as the individual components. So that was satisfactory. Next, I'd like to mention about the compatibility of the program with other software products. Engineers who have their projects drawn on CAD often find that they need to redraw their entire project in the analysis software when they come to the point of modeling and analyzing their design. GTS NX enables you to import your CAD drawings directly into the program. This feature completely eliminates the need to recreate existing drawings in the program, thus saving us considerable amounts of the time and effort. Once the geometry is imported, there is a variety of different tools to fix geometry shapes. For example, where we have gaps between edges that should be connected, GTS NX will remove these small surfaces and make the connections. Furthermore, GTS NX can import model information such as meshing, material, structure cross-section, and load and boundary condition from other MIDAS software, such as MIDAS Gen or Civil. The CAD interface transfers project data for expanded analysis requiring soil structure interaction and detailed 3D investigation such as bridge pier and tall building foundations. Model information and loading boundary conditions analysis data from the MIDAS Gen and Civil program, other MIDAS family programs, can be synchronized on the GTS NX. Element types, load and boundary conditions, analysis method not supported on the GTS NX are excluded. The compatibility range for MIDAS MST files is shown below. This is some real project application between MIDAS programs. So, in the left-hand side, you can see the building, some structure model, and you can import into GTS NX. Then you can proceed your ground modeling, finally in GTS NX. And the similar structures. And also from MIDAS Civil, using the MIDAS Civil, the bridge model can be exported into GTS NX as well. Also the bridge applications. So this is showing the some result after analysis, including the superstructure in GTS NX. Just some brief words about this kind of analysis. We believe that soil structure interaction is a key point when dealing with high-rise structures, and it is still a field that is evolving to more refined result. From the geotechnical viewpoint, the result of settlements, total and differential, the distribution of loads and bending moments in the files, the interaction between the raft and the soil, which is the file raft hypothesis, the interaction between the files, which is the group effect, are very important topics that are only able to be achieved with some accuracy when using 3D numerical modeling. So along with a platform that enables this modeling, the soil properties might be modeled with the use of soil constitutive models, and MIDAS GTS NX allows this analysis to be done with all those prerequisites. The case study is divided in 9 chapters, started with a small introduction and going to some building details. Then we go to the soil characterization that was done in the site, and we handle the file load testing program, which was undertaken, and finally we go to the model. So we start with the structure model in Autodesk Revit, then we go to the structure model in MIDAS Gen, and finally to the geotechnical model and the full model in MIDAS GTS NX. And we go to some result and some brief conclusion that we have about this project. So the building, which is focused on the presentation is a 55-story, about 168 meters tall, designed in a layered soil of low resistance. And because of the size of the building and the soil-bounded site, soil structure interaction was necessary to evaluate the settlement and the behavior of the structure. The structure team did not work with MIDAS Gen, and their platform did not export it to Revit or another. It was impossible to directly import their model. So the geotechnical team replicated the design and the structure of the same geometry, same load and load cases used by the structure team. So this model was created in Autodesk Revit. With the Revit MIDAS Gen link, the structure model was exported to MIDAS Gen, and after applying some conditions from Gen, the model was finally exported to MIDAS GTS NX, where the full model with the ground was analyzed. As I said, the building comprised 55-story, result in about 168-meter tall, meaning that one of the top 25 tallest building in Brazil. The whole structure is designed in reinforced concrete, and each story has an area of about 440 square meters. We have a total of 18 columns, which are actually structural walls because of its size, and a total dead load is about 300,000 kilonewton. Some of the building details about the foundation. It is a file depth foundation with 106 piles, CFA continuous flight over piles. So each one with 100 centimeter diameter and 30 meters long. The left has an area of about 680 square meters, and we can check the image in the left, which is on air view. By this phase, the file was already done, and what they were doing was excavating to them to construct the left. Now we move to the soil characterization. In this site, we have 5 SPT standard penetration tests close to 50 meter deep, and also 4 CPTU cone penetration test, which reaches depth close to 43 meter. So this site is located in the southern Brazilian coast, and its profile comprised layers of sand and clay due to the characteristic of its sedimentary deposit. With the result of the pH test, we can see the excess of pore water pressure starting from the depths of close to 40 meter. On the next slide, I will show you some result of file capacity prediction based on the cone penetration test. So here we are heading to the file load testing program. The static file load, just to define, it is composed by a real scale file which is tested by applying load, and by the same time the settlements are recorded for each load step, and the figure in the right shows the test scheme, which is basically composed by the test file and the reaction files. The program of file load testing was undertaken, which included 3 CFA continuous flight over files tested to the maximum load of close to 9 meganewton. The static load tests were undertaken prior to the foundation construction, which allows you better understanding of the behavior of files. The result of the file load test were compared to the values obtained by the circle approaches using method of SPT and CPT. As can be seen in the load settlement curve, there is a difference between them, and the provision of the behavior of file based on the CPT shows much closer for those measured file load tests, which distribute mostly explained because of the nature of the test, which is much more technological than the SPT. And in MIDAS GTS NX, the result from the file load test were used to define the properties of the file. It is very important to have file load test when designing the building foundations, especially tall buildings. So let me show you a little bit more about the file load testing program. These are some pictures of the test. The figure shows the file load scheme composed by consider the hydraulic jack, which applies load and that reacts against the reaction frame. In this case, we had 4 reaction files to resist the force. Also, the important equipment is the load cell, which allows us to read the load more accurately. The geotechnical engineer start with the design of the file load test. So we define the type of file, the diameter, the length, the maximum test load, and also the reaction system. We followed up the execution of the test and later interpreting the result. Now heading to the structural model started in Autodesk Revit. As I said, the structural team did not work with Midas Gen, and in their platform, you are not allowed to export to Revit or some kind of file that could be imported by MIDAS Gen. So the geotechnical team replicated the design structure with the Revit by using same load and load cases used by the structure team. And this model was fully created in Autodesk Revit. All the materials, sections, properties, analytical model, and loads were applied directly in Revit. I will show you a little bit of Revit interface now. So this is Autodesk Revit, and we have our full model of building here. You can see all the geometry and the arrows, which are the applied load. And the thing is that we want to take this model with Autodesk Revit and to export it to MIDAS Gen. So the function, which is a link that need to be installed, if we go to the add-ins, external tools, and we have this option, send the model to MIDAS Gen. You just choose the name you are going to save it, and here you can choose the element size for slabs and walls that you are exported. Also, you can choose the unit and just click send, and it will save the MGT file. Let's back to the presentation. So this is the view of the model imported to MIDAS Gen, including all the geometry information, sections, materials, and properties. I will show you a bit of the MIDAS Gen interface. So this is just a new file. We go to the menu, import MIDAS Gen MGT file, which was exported by Revit. I choose this one that I saved before. Just take a little bit time to open up. As you can see, the message, it is imported with 0 error and 0 warning. I will just take a closer view for you to follow. You can see the mesh showed an option together with the final stage, and also shows in the menu what was imported. So in the menu, you can see the number of stories, and we have the materials that were imported. So we have material from the concrete that we have defined in Revit. You also have other sections that was all defined in Revit. You have also this information about thickness of slab and walls. Then we have some boundary conditions, some elastic link, and some beam and release, which were also defined in Revit. And let's see, we have the loads. In this case, we have just applied dead load, live load, and wind load directly on MIDAS Gen. Let's back to the presentation. So in MIDAS Gen, some conditions were applied as confirming the story information, initial boundary condition, and wind loss. And then the model was analyzed to check for inconsistencies and comparing the reactions obtained by the structure team on their platform. Those obtained by Midas Gen, the difference was smaller than 5%, which is considered a very good approach allowed with the structure team. The behavior of the model was approved and then exported to Midas GTS NX to start the foundation process. Let's back to the Midas Gen to show how to export. So we have the full model of the structure here, and we want to export this to open in Midas GTS NX. We go to the menu, export, MXD file for GTS, and just save it. And later we can open it in Midas GTS NX. Let's back to the presentation. Going on to the geotechnical model inside of Midas GTS NX, soil meshes were created in square 100 meter by each side with 50 meter of depth. Soil layers were created based on the type of soil and resistance. For this case, we have created 7 different layers. For sand, the failure criteria used was the Moore column, in which the result of soil investigation may provide a good provision of values of friction angle. And for clays, the constitutive model used was modified Chemplay model, which is more complex one with some properties are not defined very easily. About the file Raft, we have the 3.5 meter thick Raft and mesh it as a solid element. And the material is concrete, considered fully elastic. Along with the Raft, we have 106 files which were meshed as line to solid interface. Let me show you the model in Midas GTS NX. So let's check it out first, the model itself. We have all the soil layers. And let me show you the left and the files. So all the 106 files and the 3.5 meter thick left. Let's back to the presentation. For the file model type, there are some ways to work with files in numerical models. The best way would be to consider a file as solid and find the interface properties and simulate this behavior. But the problem is that the model becomes too heavy to analysis. So a solution that also can be done in Midas GTS NX is to consider the file as a lot of element beam type. So converging a line to beam and creating an interface to simulate its behavior. So the model is equal to the soil, which is composed by a solid mesh plus the files, which are lines converted to beams and interface line to solid. Let me show you the file is actually just lines that are converted to beam. So they have a cross section and also they have properties of a file. So we can specify what is their behavior. So trying to obtain better values, we put them a file load test calibration. In Midas GTS NX, we have created this simple model to calibrate the load settlement behavior. So the geometry of the file will reproduce different load steps, and the file parameters were changed through trial and error. That is what we call a class C prediction, where parameters are changed looking for convergence with measured values. Load settlement curve shows the file load test result along with the finite element model created, and the values of settlement seems to fit well to what was measured. So some numerical models of building foundations are made only by applying load or pressure at the base of the columns. It is like retreating the lowest values for each column from the structure team and apply it directly to the model. This might so neglect the retribution of loads in the superstructure and its stiffness or rigidity, as you wish. So those results of from the real behavior of the structure showing higher values of differential settlements. Looking to our model, if we try to create a full model, which is the soil plus the pile left plus the structure. And as was said, it is understood that differential settlements behavior seems to be closer than when using other kind of models. Another advantage is to be able to evaluate different load cases directly and also wind load. Let me show you the complete model here. We have the pile left and the building, which is the superstructure, and all the soil layers, 7 soil layers that we have created by this case. Now, heading to the first result, we have selected here the total settlement. The preliminary analysis tried to satisfy the maximum settlement criteria defined previously for the host structure, and the analysis of differential settlement is known, and also calculating the angular distortion, which tends to be more important. As stated before, this model is working with the whole superstructure attached to the foundation. The result of settlement, especially the differential settlement, tends to be more real due to the stiffness and rigidity of the superstructure. Let's take a look at the result. Let's see only the files. In the displacement result, we can check the values of settlement in each file. You can also select each file node by its tab and export these values of settlement. Here in the presentation, we have called the settlement as delta. Here in the next slide, showing the result of file loads and the distribution of load along the file. So it is important to note that file was located in different spots along the left to have different loads acting. And this can be evaluated through this analysis using the values of loads obtained to each file and divide by the settlements for each file. So we can calculate springs. Those springs are different for each file. The reason of this is mainly because of the position of the file inside the left, which can be affected by a location of the column. Due to file group effects, which tend to decrease the performance of the file, meaning that some may not offer the same reaction as others. So the generated springs for each file may be sent to the structure team or simply export back to Midas Gen. And the very same thing can be done for area springs. This is a file left hypothesis. Values of pressure above the left might be divided by the settlement update in the same point. So this also might be sent to structure team or exported to Midas Gen. So taking a look in the result of actual force in files, as the same left I have said before about extracting those values, we can extract the value of each file. So these values can be posted to Microsoft Excel. So we can calculate the spring and it is easily sent to the structure engineer. Another set of results are the values of bending moments in the files. So these values are particularly important to define the structural design of files. As these files are continuous flight over files, the reinforcement case and the length are very important to be defined, as there is particularly to insert reinforcement when length is over 12 or 80 meters. So special procedure might be required as special concrete and also vibrators attached to the cage. So the result might be particularly important when dealing with wind load cases, which this case gave me to imply higher values in this situation. So let me show you the result of bending moment in the files. We can check the bending moments in the files here. Some sides of the left are much higher than from those by the files in the middle. Finally, some conclusions. We consider that we had a successful interaction between Revit, MIDAS Gen, and MIDAS GTS NX. And the key result from MIDAS GTS NX that we have analyzed are firstly the settlement of the file left foundation, which might be inside a range of the tolerable settlements for this kind of structure. For interaction with the structural team, springs can be created either for each file and also as spring area springs, which are the contact of the left with the soil. So this kind of information might be repeated, selecting the correct nodes and exporting the values of loss and settlement. So dividing load for settlement and we have a spring. In the case of area spring, you might export the pressure and settlements and just divide pressure per settlement, then we get area spring. Normally, interaction between the geotechnical and structural teams are done by several iterations, starting with the setup load sent by the structural team, which result in a set of springs calculated by the geotechnical team. Convergence between both models are being sought, and sometimes several iterations are needed for that. By the time full model established using same platform, the number of iterations needed to converge are reduced. So we really believe that this is a good way to go. As a final comment, we need to measure, and which means that for every effort that we are trying to do to involve with complex models, we still need to match the real behavior of destruction. And in this particular case, every column of this building will be monitored for vertical displacement since the construction of the very first story. It is to make sure that we are heading in the right way. Another thought is that having some quality soil investigation to retrieve reliable parameters from the soil is crucial, and also have an instrumented file load test is crucial. So the result of our model all depend on the inequality of this information. Thank you.